Hi, so in this video, we are going to focus on period of simple harmonic motion for two systems. First one is a single spring and the second one is simple pendulum. So let's go to the first one, which is a single spring. So we have two types of single spring. We have vertical spring like this, and we also have horizontal spring. So the only force act on this single spring is restoring force of the spring. So using Newton's second law of motion, F equals ma, and the spring's Hooke's law, which is Fs equals to negative Ka, we combine these two equations together, and when we rearrange it with, and we add in the SHM's, the very first equation of SHM, which is A equals to negative omega squared x, we can get this equation, and from there we can get your angular frequency, which is the third K over m, where K is the spring constant and the m is the mass of this block. And then we know that omega is equals to 2 pi over t, where t is the period. And then from there, when we rearrange it, finally we can get this is the equation for single springs period. So t equals to 2 pi third m over k. These are all the definitions for each symbol. And here you can see that the period t and the frequency f only depends on the mass and the spring constant. They do not depend on the other parameters such as amplitude. But to make sure that these equations can be used and mass and the spring constant are the only parameters that affect the period, we have to meet these conditions. The first one, we have to make sure that the elastic limit is not exceeded. Means that when you pull out the spring, make sure that it will go back to it will return to its original shape. So if you pull it too much until the shape of the spring is deformed, means that you cannot use this equation any longer. The next one is the spring is slight and obeys Hooke's law, and there is no air resistance on the surface, and there is no friction. The next system, the second system, is simple pendulum. So you look here, this is a simple pendulum. It exhibits a periodic motion. It has a mass like this, and constant length of the string. So when we freeze it to a certain height and we put it in a free body diagram, we have tension and we have weight over here. Previously, we've been talking about the restoring force. It always tries to go back to the equilibrium point. So the restoring force is actually moving to here. Here, so this is the restoring force. So we can say that force acting on the bob are the tension and the weight. So the restoring force which acted on the bob to bring it back to its equilibrium position is Fs equals to negative mg sine theta. So this is the theta, sine theta, and this is the Fs. So Fs equals to negative mg sine theta, and when we assume that the angle is too small, sine theta is equals to x over L. Thus, we substitute the sine theta as x over L, and then we put in the Newton's second law of motion. We can get the angular frequency for this pendulum as omega equals to third g over L, where these two parameters, g is the gravitational acceleration and then the L is the length of the string. When we rearrange, we're going to end up with the period for pendulum. T equals to 2 pi third L over g. Okay, so period and frequency of a pendulum depends only on the length and gravitational acceleration of, let's say, because we are on Earth, the gravitational acceleration of the Earth is 9.81 meter per second. So the period is independent of the mass. So it doesn't matter how big or how small or how light or how heavy the mass of the pendulum bob, it does not depend on that. And also It doesn't depend on the amplitude. But there are certain conditions that we have to meet before we can use this period equation. What are those? The conditions that we have to meet are, we have to make sure that the angle is small, which is less than 10 degrees, so that we can use this equation. And then the string has to be inelastic, means that it cannot bounce back just like spring. We don't want that. And only the gravitational force and tension in the string acting on the simple pendulum. Means that when you try to release it, make sure that you release it like that, not try to push the pendulum until it has external force to the system. So yeah, that's all for this chapter. Thank you.